Welcome to the University of Idaho's Integrated Design Lab Fall Lecture Series. I am Kristen Housefight, and I'm the IDL Education Coordinator and your facilitator for tonight's lecture. We'd like to thank the sponsors for the lecture series, which are the Northwest Energy Efficiency Alliance and Idaho Power Company. In addition to tonight's lecture, this series will include 2 residential efficiency topics that will be scheduled in the very near future. One that we do have scheduled is December 6th on high performance hospitals, and that's going to be given by Heather Burpee. For those of you in the room, please remember to sign in and include your AIA number so you get your accreditation. And the bathrooms are down at the very end of the hallway on the left-hand side. And for those of you online, please email your questions to khaustveit@uidaho.edu, and we'll ask them of the presenter. And also be sure to send your AIA number to that email address as well. And finally tonight, we'd like to thank Kyle Konis for coming to talk to us about effective daylighting of high-performance buildings. Please help me welcome Kyle.
Okay, well, thanks for inviting me out to Boise. My name again is Kyle Konis, and this talk is going to cover probably a little more on methods and techniques for collecting subjective and physical data from buildings to understand performance, and the emphasis is on daylighting. But it will also discuss the daylighting performance of a recently constructed high-performance side-lit office building. So it's been a while since I've been to Boise. I was here quite often in high school for the jazz festivals, and it was interesting to me to sort of see the transitions that a lot of cities are going through to become green and more sustainable. So I was noting the bike lanes, and then I caught my eye, which was a gentleman who's created a bicycle car, which he is piloting through the city. So I was very impressed with that. And I was recently teaching in Portland, Oregon, and this sort of fits right in with what's happening there. So going on to daylighting in buildings, the building facade is one of the major impacts on building energy concentration, going beyond just to daylighting to controlling solar loads to reduce air conditioning energy use in buildings. And also to minimize electric lighting and the heat loads associated with electric lighting. Then we can account for 57% of the energy profile, the electricity profile of a commercial office building could be attributed to some aspects of the design of the facade. And so when we're talking about daylighting in buildings, one of the challenges of effective daylighting is balancing a number of different performance aspects going beyond lighting to address solar control, occupant comfort, and the integration of lighting systems that are capable of dimming in response to daylight. So commercial buildings in particular, commercial office buildings, are really good candidates for daylighting. And one of the reasons that we focus on lighting particularly, this is the daily energy profile from California, is that the capacity, the number of power plants that have to be operational are sized to this peak load. And when that peak load exceeds the generating capacity, that's when you start to encounter blackouts. And so one of the interesting elements of lighting and fenestration is that these sort of peak uses, the energy loads that are happening in the afternoon when California is experiencing peak demand are lighting, air conditioning, both residential and commercial. And so this is really, I think, where architects can come into play to help shave off this peak demand by controlling solar loads both in commercial and residential buildings, but also minimizing electric lighting use. And that should seem like a no-brainer for buildings that are occupied during the daytime. We should make ready use of available daylight outdoors. So as I was chasing the bicycle car down the street to get a photo, I noticed that a fairly common kind of building outcome, this is the US Bank Tower, but this could be a building in Portland, Oregon, this could be a building in San Francisco. Many tall office buildings, when you look at these during the day, you see the perimeter electric lighting. All of those fixtures are on adjacent to the windows. And that has to do with the zoning of the lighting system when it was designed. Typically very little granularity in the control of these systems, just in terms of how they can be switched on and off. But also the lack of photo controls. There's still very few buildings in operation that have lighting that's even capable of being dimmed in response to daylight. But this building and the adjacent building, the Wells Fargo building, start to bring up some of the problems that more recent buildings have tried to address and glazing technologies have tried to solve. So here the solar control, rather than having a glazed facade that has a lot of the blinds down, this building uses a tinted glass, which reflects a lot of the solar component, but also limits the available daylight indoors. So here we have very little visibility into the building, but you can see, at least from my screen, that the lights are also on in this building. And in this case, they may need to be on due to the lack of daylight availability enabled by the facade. So in more recent buildings, particularly buildings that are promoted as green or high performance or sustainable, nearly all of these buildings claim the use of daylight as a mechanism to both meet energy objectives of the building, but also to enhance the indoor environment. And that's increasingly more common in the language that's being used to promote these buildings. They're promoted as transmitting or maximizing the amount of daylight into the building. And that's typically done through large window-to-wall ratios, specification of high visible light transmittance glass, and hopefully the inclusion of photosensitive lighting with photo controls. And there's great examples of that in this building. I notice those lights are also on right now as well. And that's sort of what this research is beginning to look at. We very rarely visit these buildings in use to understand if the design or the performance in use is meeting design intent for energy, or even more uncommon, for indoor environmental quality for the building occupants. So my research, I'm an architect, I'm trained as an architect, but I have a PhD in building science, and for the past 4 years before I started teaching, I was working with the Lawrence Berkeley National Lab Windows and Daylighting Group, looking at expanding and improving the body of knowledge that the market really uses. The design and construction industry is really extremely risk adverse to new technologies and new approaches. So if we have goals to reduce energy demand or to enhance indoor environmental quality based on the metrics that we use to judge that, we need to really have proof of performance in the field. We need to demonstrate that these technologies are performing in the field, and performance not only in terms of energy, but in terms of the end user acceptance of these different technologies. So my research looks at several different topics. One is the integration of multiple technologies in buildings. So very often it's a technological integration question, not just an evaluation of a single technology like a high visible light transmittance glass. We need to look at that both in terms of how the photo control system is designed in response and appropriately commissioned in response to the daylighting patterns that glazing enables. But we also need to look at the occupants, how those occupants may judge the space, and also how they may intervene if they judge the space to be uncomfortable. So before we can develop automated facades or automated control systems, we need to actually have the models for occupant comfort and satisfaction that would allow us to actuate those systems. And so a second topic is the modeling of subjective perceptions of daylighting and other indoor environmental quality attributes to build these models so that we can then design buildings around them to achieve successful outcomes. A third is the development of tools, simulation tools that can be used early in the design process to improve the decision making that very often happens very early in the design, but before the design, all of the decisions have been made. And then finally, to influence both building codes, but also the voluntary compliance criteria that's becoming increasingly important to achieve. This is becoming the LEED system, for example. The EQ credits are becoming a kind of a default performance goal, but these were never meant to influence design. These were meant to be the kind of compliance criteria that set the bare minimum. Very often, these are now being set as performance objectives. And we need to look in a much more sophisticated way when we're looking at daylight beyond these basic indicators. So my work looks at research projects that feed this body of knowledge, and it's those projects are done in several different arenas. The first with the Lawrence Berkeley National Lab, we're in full-scale test sites, and there's a lot of information that we can collect from studying systems in a very controlled condition, but still enabling the systems to be evaluated in relation to multiple technologies and the integration of those technologies, but also in response to real physical environmental conditions, real sun and sky conditions, real sort of weathering conditions, seasonal changes in sun and sky conditions, and in a space that's full scale, so we can go in and appraise those conditions from an end user perspective. There are limitations with these test sites in that we're very often making assumptions for how people would judge these technologies, because it's very hard to get people to work in these test cells for extended periods of time. So field studies enable us to really get proof of performance in real operating conditions when people are performing real working tasks. These are very often opportunistic studies, which are more difficult to perform in many cases. But getting access to buildings in use, I think, is really important for both proving the performance of those buildings, but also refining the knowledge and assumptions that designers use when they're designing daylit buildings. So my research specializes in the development of new tools, diagnostic tools that allow us to get rich, detailed occupant feedback data in the field that we can use to inform our decision making. So at the lab, and Kevin and I have been talking a lot about luminance-based metrics with our work with the IES. This is some results from a study looking at interior shading systems and light redirecting systems. Buildings in use tend to, particularly buildings that have large solar exposures, tend to have a lot of shading use. And so if you're not evaluating the building in terms of its performance with the shades down or partially down to control solar loads on occupants or to create visual comfort, then you're not doing a very realistic assessment of the daylight availability in that space. And so this research was looking at how these shading systems can perform in intelligent ways, in more sophisticated ways, to redirect daylight to make more uniform light distributions and to control glare. This was predominantly a visual comfort study to look at how to maintain comfortable visual working conditions while still allowing sufficient daylight to offset electric lighting. So you'll notice in almost all of these that controlling solar loads to maintain visual comfort, with the exception of the roller shade at the far right, yields a very limited view. And these are dynamic systems. Many of these are adjusting their tilts and slat angles automatically. So this view isn't blocked the entire day, but that's another performance aspect that's very rarely considered. Maintaining visual comfort and view at the same time is very challenging for highly glazed buildings. Test cells also enable us to look very specifically at light redirecting technologies relative to a base case, and so we can configure these rooms. In this case, the upper aperture was left open to test the light louver system, which beams light across the ceiling rather than down into the field of view. So we were able to use the HDR camera, which I'll talk a little bit more about, to create a kind of a pixelated map of the ceiling and then start to look at the light distribution across the ceiling, essentially comparing that to the equivalent of a fluorescent light fixture that would then be a light source from above rather than from the side, which is really the way we've adapted from an evolutionary perspective to expect daylight to be distributed. So moving on to field studies, the goal of a field study is typically to examine buildings in use and use that knowledge somehow to refine design and decision making. So going back to this latest wave of green buildings, highly glazed buildings, high visible light transmittance glass, this project looked at the San Francisco Federal Building, which is a building located in the Market District of San Francisco. And this building is similar to a lot of recent buildings in terms of the way it's described as a transparent skin, both in terms of kind of a symbolic transparency for the transparency of the government, the idea that the public can see in and sort of see what's happening inside of the building, but also transparent in terms of physics. It's physically as transmissive as possible to daylight, both through the optical properties of the glass, but also through the aperture area. It's full floor-to-ceiling high visible light transmittance glazing, which allows, in this case, 67% of the visible light incident on the facade to pass through it. So this building was really considered to be a prototype of sustainable design, of green design, and daylighting featured very prominently in this project. What's interesting to me is that I've found at least 3 books that have this building, the Northwest Facade in particular, on the cover. These are buildings that say green architecture, integrated design, high performance building. But if you look through these books, there's no data from the building in use that validates these claims. And this is common, I think, in a lot of architectural publications, that the performance of the building is assumed based on the statements of the architect, or because of the rules of thumb or the materials or the technologies that are deployed in the building. But we need to go into these buildings and examine what are the real performance outcomes and how do they compare to design intent. And I think this is particularly important for buildings that are setting a precedent or trying to go away from the kind of standardized approaches that many buildings are designed around. For these buildings, I think it's very important to recognize that the designers are taking risks and sort of help in that process by providing feedback. And so the gas mileage image there was to show that it would be great if we had a metric for buildings that was as simple as gas mileage is for cars. EUI, or energy use intensity, that might be that gas mileage indicator. But when we're designing buildings for people, and so it's really easy to make a low energy building. You could make a building with no windows and no lights on. There's really no barrier to energy efficiency. The real barrier is the balance between energy efficiency and still serving the level of comfort that building occupants expect. But we also need to look at occupant behavior. I think the behavior of occupants, how building occupants modify a space once they've had time to habituate to the conditions indoors, is equally important to looking at the energy performance of the building if we're really looking at how to refine our intuition for design. And those latter two, energy is very easy to measure in many cases. And there are a lot of systems and technologies being deployed to help us collect information on energy performance with greater and greater detail. We have much fewer systems or technologies or tools available, particularly to architects once their projects are built, to look at the outcome from the perspective of the building users, particularly for large projects. So this building, this is showing the glazing going up, the high visible light transmittance glass. So one of the basic assumptions of this building was by raising the floor-to-ceiling height, you could have greater daylight transmission to the core. And so this is a basic kind of rule of thumb that the daylight zone extends as you start to extend the window head height. And I just want to acknowledge that a lot of the data that I'm showing comes from my PhD work, which was supported by LBNL, but also the T.Y. Lin Foundation, the ASHRAE Grant and Aid, the IESNA San Francisco chapters, Thunen Memorial Scholarship Fund. So all of that supported the development of the tools that I'll be showing here, and my support. So in addition to daylighting, the building floor plate was really informed by a goal to do natural ventilation. In San Francisco, natural ventilation has been made more difficult due to fire codes, but this building, because it was a GSA project, was able to sort of trump those local codes and make an argument that you could actually have a building, a high-rise building that could have windows that open. So this building has a narrow floor plate. This is primarily to allow cross-ventilation. It has active thermal mass, which just means that the concrete is exposed to the room air. And at night, they use a night flush ventilative cooling method to open these clerestory windows open automatically to allow airflow to move. The Bay Area climate is quite cool at night, and so they move that air across the ceiling, cooling that slab down in the evening, and then flushing the heat out and having that slab pre-cooled during the day to moderate the indoor temperatures without air conditioning. So for that system to work, the building had to provide adequate solar control to avoid overheating of the structure. So there's solar control could be also considered for overheating of the occupants working along the perimeter. But in this case, it was based on a sort of large scale look at the energy modeling implications of having direct beam hitting that structure without any solar control. That night flush cooling wouldn't be capable of rejecting those heat gains for periods of the year. So these facade systems were developed both to control loads on occupants, but also to make sure that cooling strategy would work. And in returning back to natural ventilation and floor plates that work well for natural ventilation, this was really referencing a lot of buildings built before World War II, which during that period, office buildings did this by default. They were long kind of alphabet-shaped buildings that used daylight and natural ventilation as the primary environmental control mechanisms. And this was largely due to the lack of available commercial HVAC and the lack of widespread deployment of fluorescent lighting, which had a much lower heat component compared to the incandescent lighting that was being used at this time. And so based on those limitations, those technologies weren't available. Buildings had to be more thoughtfully designed in response to climate, and that really limited that floor plate depth. So after the war, this is the Libby Owens Ford Glass Company building, and this starts to show the change away from these long linear floor plates to very, very dense buildings which have dramatically larger energy footprints, because as you get away from the facade, the environment can't provide the same level of services. Mechanical systems start to dominate. And you also get this interesting separation of perimeter and core zones, where the core loses that visual connection to the outdoors, but also the connection to the transient conditions that would be experienced if you had a view to a daylit environment or to environment that's ventilated naturally. You'd have a sense of the time of day, the outdoor weather conditions, movement. All of those things that we now know are very important for health and well-being. So the federal building, by moving the perimeter zones back to or the open office back to the perimeter zones and putting the cellular offices in the core, was really addressing some very important issues that were being discovered from these older building types. So to do that, it has occupants working very close to the facade, and this is the southeast facade, which uses a perforated metal scrim. This is a 50% openness factor on axis, so that cuts off half of the solar radiation. Then the glass has a solar heat gain coefficient of 0.39. So already two layers that are controlling solar radiation for occupants. But based on the building in use, there were two decisions that were made fairly quickly to retrofit the building with solar control film to reduce that beam radiation again by a factor of 0.34. but also the introduction of roller shades, and that was done primarily for visual comfort and to additionally address that beam radiation. So really understanding for occupants working adjacent to windows, that opaque wall actually plays a very important role in terms of giving the occupant a comfortable environment to work in thermally. When we're working next to fully glazed facades, we have to be very careful about the solar conditions that occupants will tolerate. So this, after the building was retrofit, this was the incident. Solar radiation was about 35 watts per meter squared, and that's with the shades up. That's what the roller shades retracted. The northwest facade uses vertical louvers. So this building is oriented almost exactly 45 degrees. So these are northwest and southeast facades. This facade you would typically see on a sort of western exposure with low angle sun. But these are also translucent louvers, so they intercept beam radiation, but they scatter that radiation and light, and so it diffuses the light. And this is a facade that was not retrofit with a film, but it did have an interior roller shade that was then added to, again, improve comfort conditions for occupants. So part of this study was to look, now that occupants had more control and management over the facade, how did they operate those shades, and what was the resulting daylight availability indoors. And then finally, this is the typical average climate conditions for San Francisco, which is really excellent for passive cooling, because the ambient outdoor temperature on average is typically lower than the comfort range in the building, which means you always have this available cooling, even in September, which is the sort of peak overheating condition in San Francisco. You always have this great Bay Area air that you can draw on to cool the building down. This is the view from the federal building. It was able to be built much taller than a lot of the adjacent buildings. So in addition, the study was examining the resulting views once the facade had been retrofit, what was left of these spectacular views. So this building was designed with very ambitious energy performance targets. It also achieved the LEED daylighting and view credits. And the daylighting is primarily done here through the visible light transmittance glass and the narrow floor plate. So looking at the daylight transmission once the building is occupied to the core is really the kind of canary in the mine shaft for how this building actually performs in terms of daylighting. And so I think one of the problems just in general for design is we have very little information from buildings in use that can give us real useful criteria when we're designing to understand what the lighting and glare conditions are that will be acceptable for building occupants to work with roller shades up. And that's actually very important for daylighting, because nearly all buildings, whether they have them or not, will eventually be retrofit to create comfort. So we have to know what visual comfort is in buildings as we're designing them. And I think we can only do that from learning from buildings in use. This is also looking at some of the behavioral modifications that can be used to inform the interior layout of spaces, but also to refine the way that the facades are designed to provide, in this case, a complete cutoff of direct view of the solar disk. But also, a lot of workstations were being modified to control glare, which was actually coming from elements of the building, for reflecting off of the metal scrim or reflecting off of the vertical louvers. So this study looked specifically at visual comfort, but also shade control behavior, physical and subjective assessments of daylight sufficiency, and electrical lighting energy reduction. And in buildings, primarily we're looking at the balance of visual comfort with energy objectives. So the real golden chalice for daylighting is to achieve visual comfort throughout the building and still achieve the electrical lighting energy reduction that's important for energy. And if we don't achieve that, then it's important to learn from these buildings what kind of indicators can we use as we're designing the buildings, glare metrics, luminance contrast ratios, simple measures of vertical illuminance, how do these indicators actually play out? Are they actually useful when we compare them to occupant subjective assessments? So this tool, the desktop polling station, was developed as a way to kind of take these controlled lab type studies that are often done in controlled settings with test subjects and actually move that into the field, into real buildings where rather than having test subjects, we have study participants who are still completing regular work tasks. They're under the same kind of level of stress to complete their job during the day. And so there's a real challenge of getting building occupants to participate in these types of human factors studies. So a big part of this investigation was to look at novel methods to collect feedback from building occupants that didn't become overly irritating over a period of weeks or distracting from their work tasks. So just to put this in context, there's ongoing research looking at what the expected or anticipated level of daylight in buildings should be to create the sense of sufficient daylight or daylight sufficiency. And is there a sort of upper threshold? There's a proposal that 2,000 lux starts to indicate excessive daylight, which then may be associated with visual discomfort and deployment of shading devices. So understanding this is one of the most basic indicators of lighting. It comes from the electrical lighting industry, where we were interested in horizontal illuminance on the work plane. But now we're using this same measure, but with different sort of thresholds for daylight sufficiency. So part of this study was just looking at what are the subjective assessments of sufficient daylight, the willingness to work without electric lighting, and how does that compare to these measures of illuminance. And then for simulation, particularly for the LEED daylighting credit, for any of these simulations to be valid or realistic, we have to have accurate or at least sort of realistic or evidence-based assumptions for when people will lower shades in buildings. So the simulation models have to have a behavioral component in them to look at realistically when is that high visible light transmittance glass going to be shaded by building users, and then the simulation tool can easily calculate the resulting illuminance conditions. But this is really the method that we should be using both for LEED, but also for our energy calculations for building codes. If we really want to claim 30% energy savings from daylighting for whole building energy savings, then those simulations really need to take into account the way buildings are operated by their occupants. So one of the objectives of this study was to look at these glare conditions in the building, and particularly from the core zone. This is a very difficult condition to mock up in a test lab because you need a large space and you also need a large open plan office. But this is a very common kind of visual condition for large open plan commercial office spaces. You have a kind of a cave-like view, or the feeling of kind of being under a freeway overpass. The light is coming in predominantly from the sides, and despite the physical quantity of light, you still have a large contrast in luminance between the window wall, which is usually quite bright, and then the floor and the ceiling, which are typically orders of magnitude darker. So this project used a field camera, and this camera was modified to acquire high dynamic range images. These are the HDR images that you're seeing here, which, if they're calibrated, give us a per pixel account of the luminance conditions and the light distribution across the space. This is just a little closer view of that same view. So this is the kind of a typical core view for occupants in the center of the building who are looking out through the northwest facade. This is on the southeast facade, looking at the penetration of the solar disk, the view of the solar disk through that scrim. And it's very interesting when you think of a 50% perforated metal screen. It looks very, very opaque from the outside, where we're seeing the light reflecting off of it. But when you're on the inside, when you're looking out, you actually hardly see that screen at all. It has almost no impact on your view, because your visual system is actually very very capable of accommodating that obstruction and allowing you to still perceive that view to the outside. So these screens, if they're designed with additional solar control elements, can actually be effective for screening solar radiation, but the visual comfort condition is still present here. So there's still a very strong luminance for the solar disk, and even with the shade fabric, which again enables a partial view, you still see a very, very bright view of the sun. And so this is a real challenge for designing effective fenestration when you have people working adjacent to the facade or within view of the path of the sun. Having either dynamic elements or fixed elements in the building that control the view of the disk, that completely block it, is really critical to both to comfort, but also to avoid all of the shades in the building being deployed. So one of the problems of doing HDR in the field is that these systems are typically very expensive. You need a high-end camera and a computer. Often a Mac Mini is used to automate the acquisition and storage of images and to process the images into HDR. So this typically limits the study because we're using impoverished research budgets here. We typically would take one camera and we would move that around the building, collecting feedback at different points in the building. But that's really challenging in the field because daylighting conditions are changing throughout the day, and each occupant has a different viewpoint in the building. So we really need a more distributed method for monitoring. And so this work looked at taking really consumer level cameras and having all of the automation for HDR acquisition happen on the camera. And so there's a technique now which I have and happy to share for converting these cameras using Stereo Data Maker, which is a firmware upgrade to enable anyone using a Canon camera to acquire HDR images. You still have to calibrate them. But this is basically a scripting process that runs on the camera. It acquires a number of JPEG images with different exposures. So each of those exposures captures the dynamic range of the camera. So it's capturing sections of the visual environment, which in daylit spaces can be many orders of magnitude greater than the dynamic range of the camera sensor. So if you take multiple images and then you combine all of the pixels that aren't saturated, either too bright or too dark, you're able to recover the HDR image. So that's done with a tool called Radiance, which is a software program, and the program HDR Gen. And that enables you to get fairly accurate HDR images that represent fairly close to the view that occupants in buildings have. And I think this is a great tool for architects to not only record the lighting conditions in buildings, but also to refine your own intuition. If you're using a simulation tool and it's giving you false color or luminance images, to be able to understand what those numbers actually mean and to judge for yourself what visual comfort and discomfort or daylight sufficiency equates to in terms of those numbers. But these quantitative measures are really useless if we don't have some record of what the occupant's perception was at that time. And so this little tool, this desktop polling station, was built to enable something that users really don't have in a lot of buildings, which is any way of actually recording their feedback, their subjective impression of indoor environmental conditions. So we could, if a building has windows that open, we can go and look at when people are opening windows. If it has shades that can be lowered and people are operating those dynamically, we can look at that as an indicator. If individual users have control over their thermostat, we could look at how they're setting that. But in large office buildings, very rarely does any individual have control over their indoor environmental conditions. That's typically done at a zone level and very often controlled by a building automation system. So this was really a way to reintroduce that channel of information and collect it and start to look at how those subjective impressions compare to our assumptions for what these numbers mean. So this was a little prototyping project that was funded by ASHRAE and IESNA, the TY Lin grant and IESNA with support from UC Berkeley to build 15 of these polling stations. And these run on the Arduino microcontroller, which is a great physical computing prototyping platform. It's originally developed by programmers, but it's aimed at designers to give designers a platform that's fairly easy to build these types of devices with. And then the rest of it was done at very low cost, built out of an acrylic light fixture. Whoops. Okay. So I just got an error report here. I'm going to have to reopen. Hope that goes back. Oh, good. And I'm getting the spinning Apple thing here. So we'll see what happens. All right, never a good sign when that happens. So apologies for everyone tuning in online. But it looks like this has crashed, so I'm going to try and okay, here we are. So the study used these polling stations at individual workspaces, and these were paired with a number of different environmental measures and the camera that was then mounted somewhere near the occupant's field of view and oriented as close as possible to their typical work task view. And I found that one of the biggest challenges for these types of survey studies is that building occupants, particularly people doing real work tasks in real buildings, don't want to take surveys. They don't, like most people, they don't want to respond to pop-up windows on their computer. They don't want to answer emails that are sent to them every 2 hours. And so that interface design issue is actually a real barrier to getting good feedback from building occupants. And I found that the design of this interface, making it something that was slightly large enough to not get lost on their desktop, but also to be at the level of sophistication of something like an alarm clock, which has a snooze button and maybe one other button that allows you some level of communication with it. This device was basically designed as simple as possible to allow someone to record their feedback without really having to be distracted from whatever cognitive tasks they were doing at their workspace. And so periodically occupants were prompted by an ambient prompt. This device starts to glow. If it's not responded to by its glowing, it has a little chirp that was actually carefully tuned to be as non-annoying as possible. But when I took this to Japan, I was actually in Japan for an energy workshop right after the nuclear disaster, working with architects and looking at techniques for early stage energy simulation. They were absolutely thrilled that this made all kinds of little sounds and chirps when you were interfacing with it. So that kind of quality to it, making it as far away from a research instrument as possible and as much a kind of fun device to have on your desk and play with, became a great way to get good feedback, but also to recruit people for the study and to get information about the building. As people started to see this device, they started to become more interested in the goals of the study and also in participating. So a number of ways of getting feedback beyond just being a mechanism that's there when they perceive particularly discomfort. There's a tool there that can record that and pair that subjective assessment with their space and the time of day, so we can actually go and put either the energy use of the building or the way the building's being controlled in context with that subjective assessment. So this study was done primarily on the upper floors of the building and was done in a series of phases. This was primarily due to the number of polling devices available. So the northwest perimeter zone, the southeast perimeter zone, and then the core zone. And each zone was, the study was repeated with multi-week phases for each interval. So one of the outcomes of the study was a discomfort glare model. And the model basically looked at the times that occupants were responding, indicating visual discomfort. And it started to look at the luminance conditions and then the patterns within those luminance conditions. And I found that some of the most basic measures of luminance, the absolute magnitude of the window luminance, the upper 10% of all the pixels, was actually driving a lot of the discomfort responses. So models built on those simple measures were actually the most accurate in predicting discomfort. But I also noticed that depending on the zone of the building, the southeast perimeter versus the northwest, the responses of people in the sort of tolerance level had a lot to do with the ambient conditions that they were in. And so in general, occupants that were exposed to brighter luminance conditions typically tended to have a greater tolerance to those luminance conditions compared with occupants in the southeast perimeter zone, which due to the building retrofits and the position of the shading devices, tended to have less tolerance for those same glare conditions. And so this shows that we really need to look at the context that occupants are in when we're predicting discomfort. And we can do that by doing an assessment of what those transient conditions are, the sort of typical transient conditions, have a impact, or we can assert that they have an impact on the acceptance of occupants. So we shouldn't be using the same model for all building occupants in all conditions. This is particularly a problem for performance measurement protocols. There's now the ASHRAE organization is starting to look at developing a consistent protocol, which is a great idea for guidelines for evaluating building performance, not just in terms of energy, but in terms of user assessment. So different levels of detail in looking at the environmental outcomes of buildings. And so they use a particular glare metric, the Uniform Glare Rating, UGR, and they set the threshold of 19 as the threshold for discomfort. And what's really interesting about this study is that number really meant two different things for these two different groups. For occupants in the core zones facing the northwest, they were actually much more tolerant of that same condition compared to occupants in the perimeter zone. So again, this metric may not yield much information for us in design until we have more information on the context for how we should be interpreting it. HDR can also just be used more directly to look at the performance of facade shading systems in very specific detail. So this is looking at the luminance conditions of these vertical glass fins. And this could also be done if this was simulated in a very photometrically accurate simulation tool like Radiance. But this is looking at the average luminance of these translucent fins, which are designed to intercept direct beam radiation and then diffuse that light into the building. But what happens is that these the peak luminance, where you would actually see the solar disk behind that translucent fin, is above 20,000 candela per meter squared. And just to put that in context, a bare fluorescent bulb is about 8,000 to 10,000 candela per meter squared. And so right adjacent to the workspace, you have these fins that are being illuminated and then become light sources themselves, comparable to bare fluorescent fixtures. And that could be an issue depending on the lighting conditions that occupant is adapted to. But the outcome in this space, in the perimeter zone, was nearly all of the occupants on the floors that I monitored that worked adjacent to these fins had the shades down and very rarely operated the shades. Yeah.
Just a question about that.
Sure.
Was the intent of the fins to provide full cutoff towards the disk of the sun, or was it to block solar radiation from coming inside the window? So this definitely looks like it's not performing in terms of what happens when the sun's directly behind it, but in a lot of the other conditions when it's blocking the sun from coming into the window, did you look at some of those other time frames as well?
Yeah, so you can, and LBNL did a study of the effectiveness of these for solar cutoff. And like a lot of static systems, it's very hard to design a static system that restricts the sun at all times of day. And so the goal of this, and this is just my guess here, there's definitely periods in the late afternoon, particularly when the sun is in the sky longer, where you have direct sun coming into the building. But quite often that's after most of the occupants have left for the day. So in terms of controlling solar radiation for heat gains, it does a fine job. But the real need here, if you're going to have an unshaded facade, is to control the view of the disk for visual comfort.
So was this a misguided solution then? They spent a lot of money for something that really didn't.
I don't want to have that be the conclusion, because almost every post-occupancy study, when you go into a building, you actually look at the performance. There are definitely aspects of the building that could be tuned, but we don't want to lose track of the overall the goals of this building in terms of daylight transmission, narrower floor plate, clear glass to enable views out. Those are all sort of steps in the right direction. But the specification of a translucent fin, I think, is getting you into a lot of trouble from a visual comfort standpoint. So it's still doing a lot of things well, and probably better than other buildings. But what's the theme of this research is that nearly all of the solutions aren't meeting the comfort aspect. And so that's starting to lead to retrofits, which then further limit the daylight availability indoors. And so in this case, the takeaway would be the translucent nature is really an issue, and simply an opaque fin, something that would be opaque but may still have glass on both sides to give it that, it would still have that reflective quality. But if it had some interlayer that was completely opaque, that would be a much better solution for visual comfort. And you would still have to deal with another issue of this building, which is when light hits glass at an oblique angle, it reflects. And so you actually get some specular reflections coming off of the fins that are taking beam radiation and basically mirroring it back into the building. So these optical components are really spectacular from the outside, and I think there's no surprise why this is probably the most commonly photographed aspect of the building. It really has this great material performance element to it from the street level view, but a lot of that aspect is really to the disservice of the comfort of the people working indoors. So I think design-wise, there's ways to balance both of those goals. So looking at daylight sufficiency, the LEED system is starting to look at a threshold for daylight autonomy of 300 lux, which is used as a kind of a cutoff for sufficient daylighting. And one of the things that I found from looking at the occupant feedback was that there was a high probability, if you asked occupants if the daylight was sufficient, each of the zones had a different response, but there was a high probability, even at 100 lux of ambient daylight, that occupants didn't see any need for supplemental electric lighting. And so from an energy perspective, this was a question that focused directly on the need for electric lighting. But from an energy perspective, there was variability between occupants for the amount of daylight they really needed or expected in their workspace. But there was also quite a bit of difference from this threshold, and I think more research needs to be done to really investigate this. But what the danger of having a really high threshold for daylight transmission is that it starts to yield these very gymnastic approaches to try and really physically maximize daylight transmission to get these credits, with less thought being put into the quality of the light being distributed or the kinds of controls that might go into place. So I found that even in the building when it was heavily shaded to create visual comfort, there was a kind of a canopy-like indoor lighting condition which still had low daylight levels, but it still had sufficient daylight for most of the occupants. You can see here the yellow responses over the course of the day are occupant responses indicating sufficient daylight. And so particularly for people working in the core, we shouldn't assume that they really expect the same level of daylight as those in the perimeter. And so I think we need to continue to start to look at what these thresholds might be, but also give individual occupants control over the light that's allowed to come into their workspace. So one of the downsides of the retrofits and the shading of the building facade was that the physical daylight condition, and this is a challenge to measure because you have, in the core zone, you have electric lighting as well. So by subtracting out the contribution of the electric light at night, you can figure out what that light is. You can recover the daylight contribution during the day. And the peak daylight in the core was 50 lux for this building among the polling stations set up in occupant workstations. And that equates to about 0.5% of the available daylight under an overcast sky, if we assume it's a 10,000 lux overcast sky. So while the building did achieve sufficient daylight in the perimeter zones, the real limitation of the facade modifications was in the core. And so this is just one way of looking at that. This is a fairly complicated chart, but this is showing a kind of a typical day if you were to average all of the days together. And you can look at the black line is looking at the percent of total light that's being delivered from electric lighting. So this is the northwest perimeter zone, and it's showing that daylight is really saturating this space most of the day. And the bars show the percent or the total number of polling stations that are meeting that daylight sufficiency threshold. And so for most of the day, you get between 40 to 70% of the polling stations are getting sufficient daylight in the perimeter zone of the building, and that's with a lot of the shades down. And then similarly in the southeast perimeter zone, it's a little more dynamic, and it has a lot to do with the position of the sun, but still achieving the daylight autonomy criteria for I would say the majority of the day before 2 p.m. But if we look at the core zone, nearly all of the light in the core zone is still being delivered by the electric lighting. And so from an energy perspective, this daylighting strategy still requires substantial electrical lighting to provide task visibility in the core, despite the narrow floor plate. And I think that's basically that's the 20 or 30-year challenge that daylighting in buildings has struggled with, which is how do you maintain visual comfort in the perimeter zone and deliver sufficient daylight to the core. Some of the light redirecting shading systems that I was showing from the LBNL test site are technologies that are starting to address that. You have the light louver here, which I think is a great strategy for that, which is a static optical light redirecting louver system. And those systems, I think, are going to start to address this. So in terms of visible light, we learned that not only did the majority of occupants maintain a fairly shaded facade, which really limits the potential of that added clerestory glass to transmit daylight further into the core, but also they rarely adjusted the shade position. So we found people tended to, and there was a range of lighting conditions. You can see here this was actually a real detailed accounting of the shade positioning with a little visualization. But at the top there were some study participants that actually rarely used the shades at all, or operated the shades but only to control direct beam. And what was interesting is when you went and looked at their workstations, nearly all of these occupants had made informal modifications to their workspace. So they were still using shading devices, but they were taking that solar control and glare control and treating that as a problem that they dealt with informally in their workstation. So by looking at the occupants that did operate the shades, we're able to develop field-based predictive models that we can then use in simulation tools to better understand and better predict when occupants would lower shades. And one of the challenges is that this is a complex facade. It's subdivided into multiple sections. So our assumptions, not only do they need to represent realistic occupant behavior, but we need to actually know when we design a building facade that enables a more complex form of interaction, how the occupants are going to respond to those different types and levels of controls that we give them. So again, a plug for more field studies and more human factors studies to actually look at those uses. But finally, if we're trying to get net zero buildings, we really need buildings that don't use electric lighting during the day. When we have sufficient light from the sky, we need to have not a reduction in electric lighting during the day, but we need to minimize electric lighting to only spaces that don't receive daylight. And so this was the efforts to get lighting energy data out of a very sort of stubborn building management system. So this is 1 week where I was getting clean data. And this shows you the effect of the photo controls. There is, if you look at the whole floor lighting energy, a lot of zones that aren't benefiting, that either aren't connected to the photo controls, but are connected to switches, but occupants aren't switching the lights off, or are just illuminating parts of the building that aren't receiving daylight. So even in a building that's achieved this floor plate that's very beneficial for daylighting, there's a long way to go in terms of the real performance in terms of a whole floor lighting energy reduction. So just a little bit on thermal comfort, because the polling device includes a operative temperature sensor for occupants working in daylit environments. We're also subjecting them to very different thermal conditions than a typical building that would have occupants working in completely sheltered and mechanically controlled conditions. So this is the assumption. This is the ASHRAE adaptive thermal comfort model. And the assumption here was that occupants would actually have an expanded comfort range based on the seasonal changes in outdoor ambient conditions, which follows a conventional wisdom that in the summer people are adapted to warmer conditions, in the winter people are more prepared for cooler conditions, and the thermal regimes, the control regimes in buildings, shouldn't have a kind of a ad hoc set point that's held throughout the year, but should actually modulate to reflect those seasonal changes in climate, which actually has huge energy savings if you consider the savings that could be achieved by less air conditioning hours, less heating hours to hit those set points. So I actually looked at this. I wanted to see if people were satisfied in this building when it actually experienced one of these heat waves. And so this is what you're seeing is the outdoor temperature over about 4 weeks, and then the indoor temperature of 15 polling stations. Those are those light gray temperature profiles. And then layered on top of that is the subjective assessments of the building occupants. And again, this is a building that's doing nighttime cooling. And so you tend to see a trend over the course of a day of a preference, a dissatisfaction and a preference to be warmer, and then a dissatisfaction and a preference to be cooler. But you're also seeing a lot of satisfied occupants over a range of different thermal conditions. So it's very hard to draw conclusions from this data looking at it, other than to see that there's some dissatisfaction, but that's common in almost all buildings. So I started to model this, and I actually found models that could predict someone's response on the polling station, whether it be dissatisfied and prefer cooler, which is that blue line, and that the probability starts to drop off as it gets warmer in the building. But as the interior temperature starts to increase, you're starting to see the probability of dissatisfied and prefer to be cooler increase. And so if you look at where those two come together, the minimal point, that's really the ideal set point for the building. And if you account for 20% dissatisfaction in either direction, then you get this set point condition, or this sort of deadband area that you want to control the building to. So these were the models that were built with solid lines come from the 3 weeks of sort of typical September conditions. I made a separate model for the heat wave condition, and what I found was that occupants actually responded differently during the heat wave. They were more tolerant of slightly warmer conditions, that whole deadband moved towards warmer interior conditions, but it also expanded. It showed that occupants were willing to tolerate a greater range in thermal conditions. So these are fairly subtle changes, but this starts to suggest that we should consider that the thermal conditions in buildings could actually be sensitive to outdoor climate, and this is something that's been common in environmentally responsive buildings for hundreds of years, but now that we're using mechanical conditioning systems, there's efforts now to reintroduce this type of control, and there's benefits both in terms of occupant expectations and comfort, but also huge potential to reduce energy use. So I'm going to wrap up here and just say that the next steps for my research is to really look at how to take these techniques, which are all still in prototype form, and scale them up to large portfolios of buildings. So I'm working now to develop a lower cost and a more readily scalable tools to do these types of studies in buildings, with an emphasis not so much on energy, but on the end user assessments of buildings. So this data has to lead to information. We have to find ways that we can communicate with architects and engineers to inform the design of future buildings. So I'm doing this now through the validation of a lot of the systems and performance metrics that are used during design. And then I think we need to scale this up. So leveraging these tools, scalable tools that we can then use to really create bodies of data and evidence from buildings in use that can be used to improve practice and to build evidence for the kinds of incentives and practices that could have a lower impact on energy use. Okay, thank you. Yeah.
Question. So you mentioned that the San Francisco Federal Building used energy simulation to help drive some of the design aspects of the building, like the solar control for the night flush parameters and stuff like that. Do you know if they did any detailed daylight simulation that helped drive the design of the solar facade as well?
So that was a big effort during my archival research phase of my dissertation, and I found very little in terms of records of that simulation work. There's sort of anecdotal evidence that some of that work was done early on by consultants, but one of the issues is that there's actually fairly broad consensus for thermal comfort performance and requirements. ASHRAE standards are well known. And there's sort of an expectation that buildings should be designed to meet those standards. There's really much less agreement on what the consensus standard is for daylighting. And as such, there's less emphasis during design on meeting those performance goals. So the LEED daylighting EQ credit may be the sort of standard now, but almost no emphasis for visual comfort. Thermal comfort is a well-established kind of topic, and so I think visual comfort has been, for a much longer period of time, really challenged in terms of its ability to sort of get into standard design practice. And I think one of the limitations is it's just a much harder kind of comfort aspect to really study and build a consensus model. And Kevin's been working on that, I've been working on it. And I think HDR imaging and the availability now of tools that allow us to do these studies in buildings will potentially help with that. Yeah.
One thing I noticed on that building was there was floor-to-ceiling glass, which the lower 3 or 4 feet really doesn't contribute a whole lot to the daylighting aspects, my understanding. If you were just setting kind of basic standards for a middle-of-the-road building, I mean, looking at something that would be more built by a smaller local contractor that doesn't have a lot of sophisticated tools and designs, what would be some of the standards you'd look at as far as floor plate depth, size of the windows, size of the floor height, in order to get penetration that would work without and maintain these visual comfort aspects as well?
Well, I think a big, and I always like to emphasize that we have all of the technologies that we need on the shelf. The the lack of effective performance in buildings isn't due to a lack of a technology that we could implement. But I think that it's very hard to recommend rules of thumb, particularly for daylighting, because it's so dependent on the particular solar orientation of the building, the adjacent context, the program, the interior space layout. But when you start with window to wall ratio as a basic kind of conversation point for architects and engineers quite often, because that's where energy loads are being massaged. And so thinking about, and California is actually going to make it through its Title 24 energy codes, they're going to make it almost impossible to do a floor to ceiling, if not already, a floor to ceiling glazed facade, particularly on facades that get large periods of direct sun. So I think that the codes are already sort of pushing that direction. But for good architecture, there are some cases where large areas of glass may be appropriate for architecture. And so the kind of performance approach enables designers to take a certain average window to wall ratio for the building that would impact its energy profile, but then use that thoughtfully across the envelope to create variation in terms of the lighting environment indoors. I think one of the daylight's very forgiving, and so I think with if you start with a 30% window to wall ratio and you start to work around that, I think the barrier then becomes the tools that you have to get feedback on what the performance is going to be given your climate, your local climate, your typical sky conditions, whether you're doing a high-rise building or a low, 1 or 2 story building. Those sort of general spatial arrangements make the biggest impact on the energy performance and how far you have to go with the sophistication of the facade. And so I think if we're talking about 1 or 2 story buildings, it's really the goals are much more easily achieved with top lighting, which again creates a much more uniform kind of light distribution and is much better for glare, because we're typically made uncomfortable by views in our field of view. And our visual system is actually designed to, even with the shape of our eyebrow, to actually provide some sort of solar control and cutoff. So for smaller buildings, top lighting is a starting point, looking at the areas of solar exposure, the south-facing facade and the west particularly, and then basic forms of solar control that were actually very common in buildings before widespread air conditioning, exterior shading devices. A lot of those can really still achieve very good performance. But I would direct you to Lawrence Berkeley National Lab has a tool called ComFen, which if you're doing a commercial project is commercial fenestration. And that will actually allow you to take a room. It's kind of a shoebox shaped room, but you can change the geometry of it. You can change the solar orientation. And it gives you access to the International Glazing Database, which allows you to switch out all kinds of different glazings with different optical properties. You can build solar shading, and it's very quick. You can learn it in a day or two. There's great tutorials. And you can actually look and visualize what the annual lighting energy is going to be, daylight availability. And I think that will be much more useful to start to get a tool that you can design and get feedback from than taking a daylighting rule of thumb of saying your daylight zone will be twice the depth of the window head height or something like that. So I hope I answered your question.
This federal building seemed like it's another, like there's this programming meets design thing where it seemed like it was designed to have corridors on the facade, but yet the cubicles ended up there. Is that just better work with the people doing the programming, or seems like I've been in a lot of spaces where it's like, why did you put your cubicle right up against this window?
So I think that's a question of you have internal space layout, and then you have a attitude about the design of the building facade, and whether the architect and the firm doing the interior layout were thinking about that, I'm not sure.
They seldom, I mean, the end user, the person in the queue is very, very seldom represented in the design process. You've got an architect that's doing it. Are they really even doing any kind of potential space planning? I think it's a real issue.
So one of the bumps I think that is unnecessary is that the kind of cubicle architecture is still a product of large, air-conditioned, static indoor spaces, and it's it's itself very static. You have typically a space where the computer goes here, and the occupant goes here, and their stuff goes here, and you can't really modify or change that. And I think workspaces are there are firms that are obviously rethinking that kind of workspace layout, but I think there's a great starting point would be to think about having people that can just simply move their work task in an easy way, which I started to notice people would do anyways, but also not necessarily happy about it, but they were actually moving their monitor, because that's the major visual comfort issue, is working on a computer monitor in a daylit space. That tends to be the killer quite often for a good daylighting. So just giving those people the ability to move that view orientation either daily or depending on, well, typically I guess it would be daily. Some people just chose to move it completely so that they're facing away from the window, but then they have no view to the outdoors either. But also people started to actually create these sort of informal shading devices within their cubicle, and that could actually be part of the design of the partition system if the designer of that furniture system and partition system actually had information about what the indoor lighting conditions were going to be. You could actually have climate responsive indoor architecture as well. And that's just another layer in the facade layer in terms of solar control, daylight redirection, visual comfort. That's in fact probably the easiest way to deal with visual comfort, is create a very nicely daylit space, but then provide people the appropriate sheltering for their visual tasks. So I think, particularly for students or for those who have the ability to kind of think about these problems in a less market-driven or process-driven way, there's a lot of rethinking, I think, that needs to be done with that interior furniture and interior space layout. But also, everything in a commercial office building is typically homogeneous, because you want to be able to change tenants. You don't want anything in the building facade to be something that would limit the internal space layout, and so that's another barrier that is a real practical concern for commercial office space, is that kind of generic quality is actually a virtue in terms of making it more flexible. So I think it really is largely an interior design problem, if we're going to stick with floor to ceiling glass walls. Okay. Yeah.
Other questions? There are no others. So this is a good argument of why energy simulation programs still are a long ways off from being able to do accurate daylight simulation and modeling that effect on the energy outcomes of the project. And I was wondering if you knew if there were any out there that are getting better at having a more behavior predictable model for doing blind control, within an energy simulation program. Or is there still, because we've experimented with it at the lab where we're going from radiance into a custom schedule for like Energy Plus or something like that. But I was wondering if you knew of any programs that had a more direct link out there, or if there are some energy simulation programs that are getting a lot better.
I shouldn't really speak to that because I don't know, but I think that Diva for Rhino has some scheduling in it. You can put in a shade schedule, which I believe works on the assumption that any time greater than 50 watts, I think you can set this threshold too, but you have some threshold for transmitted radiation, and when that threshold is triggered, someone pulls the blind down. When that threshold's then no longer met, the blind goes back up. I found that kind of simplicity as an occupant model was not very realistic. People tend to have a kind of a mass to them, and I did notice that over periods of days, over a week of a particular type of sky condition, you would see particularly cloudy skies. It would take a week or two and there would be a kind of a trend among all the shades on the building facade. But whether we can really model that accurately or not, and then generalize it so that everyone across the world can use that same model, I think is a real challenge. So I would say in the modeling process, make several simulations and make several assumptions for the behavior of occupants, and then use that when you're making your assumptions or predictions for energy that'll probably be within a range of different possible outcomes. But again, that modeling gets even more complicated the more devices we give occupants to control. One of the best things you can do with a building facade, a window, is to subdivide it into an upper section and a lower section, controlling some of the view to the unshaded upper section. But people may still choose to cover that upper section as well. So it's not only a challenge of when are people operating things, but also what elements and how are they configuring them. I found quite often people would partially lower the shade and still have a direct view to the outside, but they would cut off everything right above the horizon. So the horizon was always wherever the eye point was in the horizon, you could find where the shade would be set. So never actually fully lowered.
Follow-up question to that.
Yeah.
With the San Francisco Federal Building, do you know if they had any type of intervention where the custodial staff would actually take the blinds up at the end of each day, so the occupant would have to actively deploy them versus them being left at a certain position, consistently? Like if no one ever touches them, then they might stay there. But if they get retracted every day, sometimes EMS systems can do that. Sometimes the custodial staff can do that. Has that been found to make an effect potentially?
So that would be a great type of field study, because then you could look at the specific conditions, the solar conditions that caused them to lower them down again. But I think you'd find a lot of resistance among the occupants for that type of intervention, because in many cases occupants had actually supplemented the shade with additional opaque materials, billboards or boxes or things. So in that case, they were probably resistant to that sort of intervention. But it was interesting because the cleaning staff did turn the lights on at night to clean the building, and I actually found that a large chunk, a non-trivial chunk of the lighting energy in the building was just by one person who came in to clean the floor at night, and they switched the whole floor plate on because it has a large large control zone. So systems that actually take into account that someone working at night might not need fluorescent lighting on full power. You could actually get some savings just by dimming the light. But also systems that can control individually addressing the lighting fixtures becomes really useful in those cases, because if you have occupancy sensing, the person who's coming in at night only uses the light that they need in the space that they're in. So when we get into energy as a real performance aspect, we have to actually think about all these little things that we might not occur to us when we're sitting on our computer building our ideal model of the world. So how people use blinds, how people clean buildings, all of that stuff starts to play a role in energy. Yeah.
So one of the strategies here would be you're balancing the amount of fenestration with the type of light that you're trying to bring in. One is the view connection to the outdoors. One is the daylighting, an upper section. You mentioned separating those two and having different controls. One, whether it's a light shelf or one of those scoop things that you have on there. Any feel for what is, from a view standpoint, is what people want to see? Because floor to ceiling, I mean, I have a building and it's got some floor to ceiling segments in it, and it really, some people are scared to go close to windows because of the height that's involved. Some people are, very happy with less. Others want the floor to ceiling because it's a status thing, but it really doesn't help. What is a good visual size for people to get that connection?
Well, I think it's impacted by two things. If you start with the floor-to-ceiling glass, you almost immediately lose the panels below or the windows below desk height, particularly because desks tend to find themselves against walls pretty often, and other office equipment. So you also then have to deal with the view of the desk, which is seen from the street. You start to see all of the possessions and elements of the interior partitions adjacent to the glass, and so yeah, it's very hard to make that argument for that lowest portion, which also does very little for the daylighting, but it does let in solar heat gains, and so you're getting the solar heat gain penalty, but you're not getting any of the benefits of view or daylight. So that's almost certainly an aesthetic choice, and again fits into this attitude about visual transparency. But if you have desks blocking it, then you lose the transparency. So that one's fairly straightforward. But in terms of a view, the visual area, what I've found is that in offices, at least in environments where people are mobile, people are up and moving, they actually go out of their way to avoid a direct view out of a window. They tend to work in an environment where they have a adjacent view or a nearby view or the ability to look out if they want to. But that sense of comfort or connection with the outdoors has more to do with the knowledge that they're quickly able to look outside, see what the outdoor weather is, see what the time of day is. It has less to do with the idea, which we very often impose on spaces, which LEED also does, of looking at the workstation and guaranteeing that there's this direct line of sight right from the workstation. I haven't done these types of psychological studies, but I would like to know if people really value that, particularly in open plan offices, or if it's a view that they can get by rotating slightly, by rolling on their chair, by standing up and moving to a space which may have a much larger view to the outdoors. One of the interesting things from the federal building was, although people shaded nearly all of the windows adjacent to their workspaces, the shared spaces, the copy areas where the copier was, they had little areas to do shared office tasks. They almost always left those spaces retracted. And so you ended up getting these pockets of daylight and direct sun that, in a sense, they could see from their workstation. And so they may have still had that connection to daylight, even though they weren't experiencing that right in their workstation. So again, I think when we're talking about people, it's very complex. Opinions are formed over fairly complex environments.
I mean, you get up and down during the day. You turn to talk on the phone, work on your computer, to lay something out on another work surface. So you are turning in different ways.
Right. So I think it's
as a lighting geek, if you were designing just based on lighting,
Yeah.
what do you know on that? How would you lay out your window, your fenestration on a south or a north wall, assuming that you can have you orientate, the site is big enough where you can orient it exactly the way you want to.
Yeah, I think it's about treating the facade as more than a two-dimensional surface. So going back basically to classical architecture, or looking at modernists before air conditioning, and looking at keeping the sun off of the glass. So if you have shading that keeps the sun off of the glass, that's a guarantee that you're keeping that direct beam out of the eye of the building occupant. So you've dealt with the major visual comfort aspect. So you're doing a smaller window-to-wall ratio. You're doing exterior solar control, which is great for architects who enjoy designing building facades. I don't think that's me. Oh, that's my phone. Sorry about that. So smaller window-to-wall ratio, controlling direct beam on, so direct beam doesn't hit the glass. Or if it does, you're letting direct beam in only for short periods of the day. And then providing people with layers of control over that window. So still relatively high visible light transmittance glass, but you have multiple types of shading devices, you have a subdivided facade, and you give people control, give them the ability to have a shade that still enables some level of view, and then give them a way to completely cut off direct view of the sky if they choose to. But make those controls simple and easy to access, and arrange it in a way that occupants are able to control these without having to reach over a partition or go into someone else's workspace. So it's I think a thoughtful management of those problems. But probably the most basic thing is a facade that has 3 dimensions to it is much easier to design to accommodate comfortable daylighting, because you can take advantage of redirecting light, you can block light, you can change light from either being reflected to being diffused off of horizontal surfaces and louvers. All of those kinds of language of lighting techniques, come into play when you have more than just a 2-dimensional facade. But due to market constraints, I think, and sort of design preferences, those 3-dimensional qualities are now coming into the technologies that are in a 2-dimensional surface. So the light louver, for example, is a light redirecting device that's really trying to do that performance with the minimal sort of dimensional depth to accommodate existing buildings. 3M is designing optical coatings that work sort of like a hologram does to redirect beam light. So there's a struggle to kind of build that in, but if you had it, it was sort of up to you to do. You'd look at historic precedent for daylighting and sort of work from there.
We have a sample of the light louver product outside on the silver cabinets if anyone's interested in actually physically seeing what Kyle's talking about.
I don't work for them, or not represented by them, by the way. And I should say it's really the optical light redirecting louver, or louvers that bounce light. It's not just that one product.
All right. Well, I think Kyle's got to catch a flight at 6:15, so should let him go. But thank you once again.
I think it's a taxi. A taxi at 6:15. Yeah. Well, thank you.